Okay, good evening, everyone. We're so sorry for starting up late today. So sorry, we had some technical issue, but we're good now. So without further delay, we'll like to take the opening prayer now. Okay, so Mr. Odeme, please, can you help us with the opening prayer?
In Jesus' precious name. Let's pray. Father, we thank you for today. Thank you for this auspicious event that you have organized to give us knowledge and increase our capacity for impact in this field. We ask that your spirit will continue to lead us, guide us, direct us. In the name of Jesus, we ask that everything that will be done here will be to the glory of your name. For the facilitators, we ask for articulation, for wisdom, for understanding, for knowledge, and the ability to speak. We ask also for understanding on the side of the students. In the name of Jesus, we give you praise for all that you are said to do in Jesus' name. Amen.
Amen.
Thank you so much. Okay, so moving on, we have the opening remark by Professor Adetiba. Professor.
Okay. Yeah, I want to say good day to everyone. The facilitator, and we have two or even three today. The facilitators, the master of events, and to every participant online and those that are physically present in the lab at FEDGEN Lab 2, and to also appreciate God for the privilege to see this day. And this is the 5th edition of our Advanced Signal Processing and Machine Intelligence Research, monthly advanced research tutorial. We had the first edition in February, specifically on the 23rd of February, 2024. And the second edition, we had the second edition on the 26th of April 2024. And in that second edition, the keynote was presented on artificial intelligence as a general purpose technology and multidisciplinary data embedding. Okay, then it was a good session, and mathematical foundation of AI with Python and TensorFlow. Okay, that were the topic of the tutorial for that particular second edition. Then we had the third edition in June, specifically on the 28th of June 2024, and the keynote was given by Dr. Ishewan, and the topic was on artificial intelligence for biomedical and bioinformatics research, and it was also a very good one. And thereafter, we had the fourth edition in July, and that happened on July 26th, 2024. And in that particular edition, we continued the tutorial on mathematical foundations of artificial intelligence with Python and TensorFlow, where we had Dr. Oshin and Mr. Gabriel Sobola giving us a presentation at that one. And here we have today at the 5th edition of this monthly advanced research tutorial, and it's a continuation of the mathematical foundation of artificial intelligence with Python and TensorFlow, and to also situate properly that this event is being funded by Google through the Google Award for TensorFlow College Outreach. This award was given for 2023-2024 session, so we're still running with that funding. So on this note, I want to say welcome to everyone, and this promises to be loaded as always. Please listen with rapt attention. Let's make the whole event highly engaging, as we have always done. And I want to say thank you to the facilitator for being available at all times. So thanks, and thanks the master of events, Over to you now.
Thank you so much, sir. Yeah, so if you I think I have witnesses in the house. Last edition we had was superb. It was insightful. It was very good. And we'll continue with that today. But before we go to our facilitator for today, we have a short presentation on physical health information system. That's with Mr. Uche. Mr. Uche will be taking us on that on a short presentation of PHIS, the platform, all we need to know about that. Mr. Uche, please, you have 10 minutes. Thank you.
Good evening, Prof. Good evening, everyone. I am Naji Uche Josiah, a PhD student of computer science at Covenant University. I'm here to make a presentation, a short one, on FEDGEN-PHIS, which is the public health information system that's been running for a couple of years now. So permit me to just share my screen so I can show everyone what I'm working with here. Yes, so FEDGEN-PHIS, it's a public health information system which aims to share public health information to people that are from various walks of life, various stratospheres of endeavors. We have researchers, sharing their research in the areas of malaria, cancer, and also cloud computing research. So the aim of this platform is basically to share information to areas where public health information is usually not available, areas where they have low access to public health information, and also to kind of sensitize the public on ongoing happenings in healthcare. People from various walks of life can come on the platform, read about what is currently going on, and get informed about the various developments and happenings in the area of malaria, cancer, and also cloud computing. Such information that will be valuable in improving their health outcomes. Now, the website address is fedgen.net/PHIS. In no time now, I would go on the platform and demonstrate step by step how we can, access the platform, sign up, and also become a contributor. Aside consuming healthcare information, it's also encouraged that we also share healthcare information to others, such that we can keep improving and increasing the content on the platform. So I'll move on to the next slide now. So I'm going to just briefly introduce, which I've already done, the FEDGEN-PHIS. We also have a language translation service, which is very pivotal to this presentation. And we have onboarding of new and existing users onto the platform. And we also teach you or explain to you how you can become an author on the FEDGEN-PHIS platform. So we're moving directly to the introduction. So when you click on fedgen.net/PHIS, you are welcomed with a platform, a homepage that basically shows you how the platform looks like. We can see on the right-hand side, we can see tags. So people want to quickly navigate to information that's relevant to them. So when they click cancer, they get to see all informations and all research findings that relate only to cancer. When they click malaria, and so as many other fields that are available there, they get contents that are related to that search fields. So we have a search bar as well. This search bar basically helps you go down to the particular content that you are looking for. We also have the language translation system. Now, we are aware that public health is a benefit or a program that enables people to get information. So we are aware a lot of people from various parts of the country cannot really assimilate or understand the English language. They are better they can better absorb the information on the platform when they hear it in their local languages. So we have many languages up on the language translation translated service that enables various users to be able to read the content that we have on the platform. So when we move on to the next part, this is just a simple article that was published, and we have a number of views. It is titled "Breast Cancer Burden in Nigeria." So as you see it on this way, you can either read it or you can also play it, and it will speak out as an audio. So we have a text to speech and also text to speech service integrated into the platform. So what you do is once you click on the language translation top, you get to see various languages. When you click on it, the text gets translated to the particular language of choice. Then once you are done with that, then you can now click on play, where you can now have that read to you, the information read to you, and you get the information you need easily. So when we've gotten the content, the best way is to contribute to what is there, become a user such that you can have access to the content and also contribute to the platform. So we just have a create your account, page where people can easily sign up and become a part of the platform. Very simple steps. Put in your first name, put in your last name, your email, your password. And what happens when you click sign up is that you get a notification stating that you should verify your email. So once you click on verify your email, instantly your account is being created. Then for signing in, it's quite easy. You've already inputted your password and your email. So all you have to do is to go and put the credentials in the login form, then you can sign in. So when you sign in, the difference between when you access the site initially and after you sign in is that you get access to more features such as notifications. You can update your profile, you can become an author, and also you can see the number of likes and impressions on your post. So we can see that once you click become an author, you get to see a window, a page that describes the process involved in becoming an author. So this is basically what you get when you click become an author. Then you get given a form like this. This form basically displays the links to scholarly databases that you have. Once you put it there, then you come to select the particular status. If you are a PhD student, if you are a researcher, if you are a lecturer. Once you select any of those options, you click apply. Then you get a notification on your mail that you have been accepted as an author. So I'll just quickly run through the platform and show a very brief presentation. So this is the platform, very well designed. When we scroll, we can see the various content arranged in categories. We'll go down, we'll also quickly see the latest information, latest posts that have been posted by other researchers. We can see what is trending as well. So let me quickly just sign in, and we can see the features that we have. So now let me put in my credentials. Yes, so I'm in now. So as we can see, the various, the side on the left that shows new features that I have access to as a user. So let me just click on any category. Let's say breast cancer. Then I scroll down to breast cancer burden in Nigeria. So I click on it. I get the content delivered to me in a couple of seconds. Then it is, by default, it is in English. So I can just go to the language translation service and select, let's say, Hausa. When I do that, in a bit, we get, you see that the content has been translated to the language that I specified. So I can read from it, understand what is written, and the platform benefits me regardless of the kind of language I understand. So we have more than 5 or 6 languages on the platform. And once we click play, we can listen to the language being read from that particular language, language that we selected. So we go back to our selection to English, then we click on author. So yeah, this is where we can contribute to the platform. We have the part where we can provide our Google Scholar link, we can provide our ResearchGate link, and once we're done, we select the category that we belong to, and we click apply. So once we apply, like I said earlier, we'll get a notification that our application has been accepted and we become an author. That means we can now send our research content, our articles to the platform, and the platform gets reviewed by a couple of experts. Then that gets sent on the platform. So that's basically what the platform is all about. KPK students are encouraged to share their research. We have a couple of very diligent students that have also, sent multiple content on our platform. So we encourage people to sign up, to use the platform and engage with it. Thank you so much.
Thank you so much, Mr. Uche, for that wonderful presentation. Thank you. Okay, so before I ask the house if anyone has a question, let me ask you my own question. So you said KPK students should put up their work on the platform. So is it just for KPK students? Like, I know there are specific areas that you're working on, like the malaria, the cancer. So what if I'm not a KPK scholar and I'm actually working on cancer? Is there a platform I can access, or is it limited to KPK scholars, please?
Yes, thank you for that question. So it is not limited to KPK scholars. We can have lecturers, collaborators, and various people from various walks of life that, because the essence of it is to share as much public health information as possible to the people that need it in various parts of the world. So you can be either a KPK scholar or someone from elsewhere that you can share your content. The good part is that your content is going to be verified. It's going to be reviewed before it gets published on the platform. So thank you.
Okay, so another question. If I push something to the platform, what do I stand to gain? Is it a win-win? Like, is there any benefit from it apart from the fact that, okay, the world is going to see because there are other platforms I can actually push my work to. So is there any benefit I'm getting from pushing my work to your platform?
Okay, thank you so much. That's a very wonderful question. So there is something called public health literacy. So in a country like Nigeria, public health literacy is not as high as we have it in other African countries. So as you publish your content on the platform, you're helping to improve public health literacy in those areas specified, malaria, cancer, such that people can, get your work. And one other thing that is also very interesting about our platform is that we don't charge. Some of these platforms will have to charge you for a fee to have your content being posted on the platform. So it is free and it's accessible. And we also have the language translation service that comes to make the content available to different people from various walks of life.
Okay, thank you so much. I think the highlight for me here is that language translation service. So anybody from different parts of the country, or even the world, is not just Nigerians, right? Can have access to it. So if you don't understand English, we have your language. How many languages do we have on board?
We have more than 5 languages.
Okay,
currently.
that's superb. Yes, once again, thank you so much, Mr. Uche. Please, if you have any question for Mr. Uche, our online participants, please, you can type it, you can put it in the chat box. He will attend to it. Because I'm trying to be time conscious now. Yeah, so we are moving to the business of the day. Like I said earlier, we started on our series on mathematics, fundamentals of AI with Python. Yeah. So to have a recap, we've had various sessions. We've had like 4 sessions, if I'm not mistaken now. So just to have a recap for maybe for some of you that missed this session, or for some of you that just want to refresh your memory. So I have Dr. Oshin here to just give us a brief recap of what we've done so far before Mr. Sobola will take over. Dr. Shima.
Good evening, everyone. You're welcome today to the August edition of the monthly advanced research tutorial. So like Professor Adetiba mentioned earlier, we've been through a couple of the research tutorials since the year began. And today we'll be looking at the third part of this, of the topic, I started with, which is basically sequence modeling and looking at the mathematics behind sequence modeling. So, just as a recap, and this recap will be done by everyone here, especially those that have been here since we started. So, so I'll be asking questions, and I want feedback from, from everyone here, even those that were not there. If you have an idea, you can share with everyone. So can anyone tell us what is sequence modeling? What's sequence modeling about? Well, what are we talking about when we say sequence modeling? So I need responses. You can put it in the chat box. Okay, so we can put it up in the chat box on Zoom. Okay. All right, or anyone here present. All right, so let me see those that are online. Okay. So let's have Comfort Shomefun. Yes. Comfort Shomefun. Can you tell us what sequence modeling is? I think I'll pick people like this at random to give us answers. We're waiting. Okay, if she's not there, can someone bail her out? Otherwise, it will seem like, we've not done anything since we started. So someone should tell us, what is sequence modeling? Nobody. Oh, okay. Okay, someone is giving us a response there. Yes. So I can see analyzing sequence data and examining interactions between the objects. Yes, that's from Dr. Taufik. Thank you so much, sir. Thank you. Analyzing sequence data and examining interactions between the objects. Okay. So can we have examples of where, and then I think I want more definitions. I want more definitions of what sequence modeling is about. More definitions and maybe examples, scenarios where sequence modeling is applicable. Omolola Ademola, Nada Ahmed. I'm just trying to call the names I'm seeing on the Zoom call. Okay, so let's have more responses. Is there only Dr. Taufik that wants to bail us out? Let's have more responses, please. Can we have more responses to these questions? Perhaps all, should we say, you know, what can we remember from sequence modeling? What can we remember that we've done on sequence modeling? Mr. Uche, do you want to? You can't remember anything? Nothing. Okay, yes. So somebody is speaking. Sequence modeling is a type of computational approach used to predict sequences of data. This can involve time series data, DNA, yes. It has applications in cancer research, understanding and predicting the behavior of biological sequences such as DNA, RNA, and proteins. Yes. Thank you. Thank you very much, Faith. Naji. If Uche will not help us, somebody Uche knows will. All right. Thank you very much, Faith. Okay, so can I get one more example? One more example of, you know, a use case scenario of sequence modeling. One more example. All right. All right. Mr. Udeme, do you want to help us with a use case of sequence modeling?
A use case of sequence modeling, I would say, since sequence modeling really takes into account the order of the data that is being used, just like the RNA and the DNA are arranged in a particular order, where if there's a change in the order of the data or the way it is arranged, it affects the computation. And I would use a scenario of investigation, as it were, where maybe a video footage can be analyzed from a particular point to a particular point in order to be able to maybe know who is a culprit in a particular event, or to know who did what, maybe in a robbery scene or something like that. So that would be the kind of scenario where I believe sequence modeling can be applied. Thank you, ma.
All right, thank you so much. So I remember when we had the first class, I talked about machine translation, sentiment analysis, text generation, stock price prediction, weather forecasting, you know, action recognition, video captioning, and we showed, you know, some examples of these in some of our slides. And so today we'll be going into, and you know, we need to bear in mind that what this tutorial is about is mathematical foundations of artificial intelligence. So we are looking at the math behind these AI models, okay? And so today we'll be continuing with what we started the last time. And today we'll be looking at hidden Markov models, okay, for sequence modeling. And, you know, let's bear in mind that, you know, this is the mathematical foundation. So let's, as we're going through this tutorial, let's think of our own work, what we are doing, you know, our own research. I mean, because that's when whatever, you know, is being taught, whatever is being taken here would, you know, be applicable. If your mind is just fixed on, okay, so they are talking about hidden Markov model, okay, how does that concern me? It won't be beneficial. So as we're going through this tutorial, let's bear in mind our own research. And that's the way, you know, as you're going through the tutorial, you'll be able to, there'll be some matches. Okay. Oh, okay. Yeah. So in my own work, this is what I do. Oh, okay. This is where it can be applicable, or, something like that. So let's, have an open mind, and I trust would have a good time today. All right. So without further ado, yeah, let's just get right into it. And Mr. Sobola is ready to take us on in this session. Okay. Yes, so the next voice you'll be hearing will be Mr. Sobola's, and his face as well.
Good evening, everyone. So we want to continue from where we stopped in the last monthly tutorial.
Okay, Mr. Sobola is trying to share his screen.
So while we are waiting, so today we want to look at the mathematical foundation. In the last class, we talked about how to calculate the initial probabilities. We said that for Markov model application, to speech recognition, that we can model the speech features, we can model it, and use that using the hidden Markov model with some algorithm like the Vita-B algorithm, the forward algorithm, the backward algorithm, the Baum-Wedge algorithm, that we can use something like that. So, and we also said that for each of, like if I have a speech features, I want to find out the particular sequence that is a replica of that speech features, that we can use Vita-B algorithm to actually do that. For instance, let's say I say this is Covenant University. So by the time I process that particular speech and I extract features from it, I'm going to have the features equivalent of that speech. So those features will be modeled using the Markov model. So for the Markov model, we can have states model. We can have Markov model for states, for word, Markov model for phonemes. And for each of those states, we have the initial probability, we have what is called the transition probability, and we have what is called the emission probability. And in the last monthly tutorial, we talked about how we can calculate the initial probability. So today we'll continue with that particular class, that particular lecture. So today we'll be starting with this. So though we will not waste time on this, we'll just quickly run through this. So this is actually talking about transition after Hensley. We are going to see how this is actually applicable to speech recognition model using the Markov model. So what we have on the board there is, on the board there is, we have three states. We have state 1, state 0, state 1, state 2. Like we said in the last class, we can traverse from one state to the other. We can also traverse within a state, like the case of 800. So we can traverse from state 0 to state 0. We can traverse from state 0 to state 1, from state 0 to state 2. And we can also traverse from state 2 to state 1. So these are actually, so what we want to look at now is what will happen if you move from states, let's say we move from state 1 to state 0 after a particular time duration. Let's call it one time step. So what would be the probability? So based on what we have here, so when you traverse from state 1 to state 0, after one step, after one duration, we are going to have the probability that we'll have there. It's still going to be A10. If you look at the right-hand side where we have our A to be equals to, A is a matrix containing 3, is a 3 by 3 matrix, where we have 0.5, 0.2, 0.3, and down to 0.1. That's on the 2 by 2. That's on the second row, second column. Is an index, is a zero index matrix. I'm using Python, zero index. So yeah, so if you traverse from state 1, if you look at your left-hand side, from state 1 to state 0, we have A10. So we are moving from state 1 to state 0. So what's the probability of moving from 1 to 0? So the probability will be P01, P01. That's what we have there. So where we have Pij, open bracket n on the right-hand side, means what's the probability of moving from state J, from state I to state J? That's probability of J against I. So what's the probability of moving from state 1 to state 0? So that is A10. So when we go to the next slide there, we have here that the first example there is saying that what's the probability of reaching state 2 from state 0 after one step? State 2 from state 0, that's from 0 to 2. So what's the probability of 0 to 2? That's probability of 2 given 0. That's the interpretation there. What's the probability of 2, state 2, given 0? So when you look at what we have on the board there, on the top of the right-hand side, we have 0, 1, 2. That's the first row there. And on the first column by the left-hand side, we have 0, 1, 2 as well. So what the interpretation of that is, the first 0 on the first column, on the first row on the top there, with the first 0 on the first column there, is saying that what's the probability of moving, what's the probability of 0 given 0? Then the next one, what's the probability of 1? That's the 1 on the row there. What's the probability of 1 given 0? And the next one is what's probability of 2 given 0? That's probability of 2. What's probability of 2 is a conditional probability. What's conditional probability of being at state 2 given state 0? That's moving from state 0 to state 2. So write that as A02. That's probability of moving from state 0 to state 2. So what it means is probability of being at 2 given state 0. So probability of being at 2. So when we compare the matrix that has A00 variable with that of numbers beneath it, we'll see that probability of being at state 2 given state 0 is 0.3. Probability of being at state 1 given state 1 is 0.2. Probability of being at state 2 given state 2 will be A22. That's 0.1. So yeah, the idea behind this is if it is after one step, we are going to have the result as what we have on our A equals to that. But if it is after n step, where n can be 2, 3, 4, or 5. So what we are going to do there is we are going to square that matrix. So before we get to that, so what I have here is just a traverse. That's what will actually happen. When we look at the first one example there on the left-hand side, we have probability of moving from state 2 to state 1. That's what probability of being at state 2, given that we have state 0. And that is the first row, first column of slide 26. That's, sorry, of slide, first row, third column of slide 26. That's 0.2, 0.3. That's probability of being in state 2, given state 0. But if the question says that what's the probability of being in state 2 given state 0, that's probability of moving from 0 to 2 after 2 time steps. So we are going to have this expression that we have there. We are going to have A01 times A12 plus A00 times A02 plus A02 times A22. So how do we get this? It's very simple. It's not difficult. Probability. So when we look at the left-hand side of this figure 10, well, don't forget that what we are doing, we are trying to lay the foundation for the ED Markov model. We are going to very soon we'll leave this and go into the real work that I want to do. I just want to quickly lay the foundation here. So now the first thing there we have A01, A12. When we look at the left-hand side of that figure 10, probability of being in state 2, that's moving from 0 to 2 after 2 time step. Moving from 0 to 2, when we look at okay, so probability, I actually wanted to get something like a pointer that I can use to point to what we have there. So probability of moving from state 0 to state 2, that is A02. When we look at that, that's top right, that's A02. Okay, because okay. So when we look at this, so probability of moving from state 0 to state 2 after 2 time step, we can move, just see my cursor there, we can move from this pass. Then on getting to 2, we can traverse because there is a self loop here, A to 2. So we can traverse at this A to 2 and be in state 2. That's one way. The second way is we can go from state 0. We can traverse from this state 0 itself. We can traverse from this state 0. That's the first time step. And in the next second time step, without go through A02 to state 2. The third way is we can go from state 0, following this path to state 1. From there, we follow A12 pass, A12 pass to state 2. I repeat, the three directions or the 3 paths that you can follow is this. From 0 following A02, then we take a self loop, A22, then we end at 2. Or from 0, we first take a self loop, A00, then follow A02, we get to state 2. Or we follow from 0, we follow this A01, then from there we follow this A12 and we get to state 2. So we are going to multiply these 3 probabilities. That's what we have here. So that's what we have on this screen here, on this side here. So when we multiply that, we have 0.22. So we have a way to actually extract that out here. That is A00, A01, and A02 multiplied by a column, a row matrix multiplied by a column matrix, A02, A12, A22. How do we extract this out? We are moving from state 0 to state 2. State 0, so we take this horizontal as the reference point from state 0 to state 2 here. State 0, that's 0.6, 0.2. That's what we have on this next slide. Okay, I don't have that here. So we have, so from state 0, so here, okay, we have it here, A00, A01, A02. So from state 0, that's this place here, to state 2. State 2 is this vertical column here. So that's why we extract this row and this vertical column. So it means that if we are moving from state 1 to state 2, we are going to multiply this row by this column. That's what we are going to do. If you are going from state 0 to state 0, we are going to pick this row, this column, and this row. If you are going from state 2 to state 1, we are going to pick this row and this column. So when you do that, you are going to have your results. But we now have an approach. We can see that as the number of time steps increases, the complexity of this particular approach, because it's like a brute force, you are using all the paths that you have there. So the complexity keeps on increasing. So we now say that in order to increase the speed of our algorithm, so what you just do there is just very simple. You just take, if it is after 2 time step, you take the square of that matrix. So when you take the square of that matrix, you are going to have what we have there, 0.4, 0.38, 0.2. So the interpretation of this is what's the probability of moving from state 0 to state 1 after 2 time step? That is 0.38. What is the probability of moving from state 0 to state 2 after 2 time step? That is 0.22. If it is after one time step, we are going to use this particular one that we square, which is 0.3. But after 2 time step, we are going to have 0.22. But if you are still doubting, we can actually confirm using this. But like I said, as the number of time step keeps on increasing, it's going to increase the complexity of the algorithm. So that is why we normally follow this approach. We square the matrix to actually do that. That is the idea behind this. And we notice here that for this particular matrix A, as the number of time steps tend towards infinity, the value becomes constant. That is actually an observation as far as this algorithm is concerned. So for any matrix that you have, as the number of time steps tends towards a larger value, you will notice that the value you are going to get, the result you are going to get will be becoming constant, just like what we have here. And this is a Python code that we have here that we can use to run that. So we want to quickly launch the FEDGEN Jupyter to actually see the result of this. So we have so here is the matrix multiplication that we have here. So here you can see that we have 3 while loops that we actually use to actually achieve this. So we can see that we have our matrix at the bottom here. We have the matrix is a 3 by 3 matrix. So the approach here is I store the matrix inside a list, initial list, and in the first loop I take the matrix out. So the reason why I did that is this algorithm will always take out the last value that was computed. So it means that if you have a 3 by 3 matrix and you multiply it by itself, so what you get is store it again inside this ls. That is what I did at this point here, ls.append lsc. So this lsc that I have here is actually the result of the first multiplication of this matrix A by itself. So you store it inside this ls. So once you store inside this ls, at the next iteration, we are going to pick the one at the back. We are going to pick the last element of that ls, which is the previous result that we computed. So this is where you're going to pick it out again. That's at the next iteration. And we are still going to multiply. So we can see that I have LA equals to MART here. So it will always be multiplying this matrix at every time. So this is just a matrix multiplication and nothing more. That is what we have here. So, but you can use, if you know how to navigate around Python very well and use the NumPy matrix function very well, inbit function, you can actually use that to reduce the complexity of what you have there. So that is that. I don't want to waste time on this because we still have some other that we want to look through. So the code will be made available to us. So if you have any questions, you can make it known to the facilitator. We'll attend to your questions. We are trying to save time. So today, this is where we have the real business with today. So here is an HMM, the ED Markov model. So what we have there is we have different kinds of model. I want us to pay attention very well, please. We have what is called the ergodic model. We have what is called the left to right model. We have what is called the Bacchus and linear model. So when we have our speech, when we extract features from the speech, so the first thing we do there is we distribute these features. We model them using states. So like the first one, for instance, there, like this last one there, that's the linear model. It could be representing a single phoneme. That's probably like C or B. So a single phoneme B can be modeled using 3 states, 4 states, 5 states, depending on the complexity of the data or what you have in your futures. So you can model that using the states. So the states here is actually, so on each of those states, like the bottom one there, the one there, like this linear model, this one here will be representing a particular set of features. You are going to have as many features inside this one here. Inside this 2, you are going to have as many features inside of it. Inside this 3, we are going to have as many features inside of that. Inside 4, we are going to have as many features inside of that. So what is going to do that is what is called the Gaussian mixture model. So the Gaussian mixture model is going to distribute those features within each state. So in a Gaussian mixture model, we use what is called mixture components. So if we have, let's say for instance, we extract 39 ms within each frame, we divide the speech features, we divide the speech. From the speech, we extract the MEL spectrogram. And from the MEL spectrogram, we divide the speech into, before we extract the MEL spectrogram, we divide it into frames like section. And within each windowed frame, that is within each frame, we extract some features sharing boundary with other features. That's why we use window. So we extract some features there. So those features that we extract, those speech feature that those speech representative that we extract, we are now do analysis on them. That's frequency analysis, and extract what is called the MEL spectrogram. So the MEL spectrogram per each frame is 39 MFCC, 39 MEL frequency. That's if you are using MEL frequency subtract coefficient for your analysis. So we are going to extract 39 MFCC per frame. That's if you are using MFCC as a feature extraction. So here, so from the 39 MFCC, we are going to have 39 MFCC in different stages. Maybe we can have like 20 of, let's assume that we have 20 of them. So maybe 5 of them can be distributed within these states, state 1. We can have 5 of them distributed inside this state 1, depending on their features. Maybe the first one is having features like maybe the variability of the speaker, maybe the environment, the noise, maybe the prosody, or maybe the accent of the speaker. Maybe that's what those particular features are they actually describing. So in other words, this state here can actually be modeling word. It can be modeling phonemes. So if I use this linear model to model phonemes, let's say let phoneme C, and I want to form, let's say I want to form phonemes, I want to form a word, maybe tab. So I'm going to have another linear model that will model A. That's A. I'm going to have another model that will model phonemes B. So to make a word out of that, I'm going to merge all those model. That's maybe the first phonemes is a 3-state model. Maybe the second one is a 4-state model. Maybe the last one is a 6-state model. I'll join them together and form words out of it. So we can see that we have different model that we use to model phonemes or words in our speech recognition. So for the ergodic, it means that there is always a transition from one state to the other, like what we can see here. Like the one we have on top here, we can move from state 1 to state 2. We can move from 2 to 3, 3 to 2. We can move from 2 to 4. So all the parts, they are well connected. All the parts are well connected. So it's an irreducible kind of model that has all the parts connected. But for the second one, so this first one is not mostly used in speech recognition because of the complexity. So, but the last 3, they are mostly used in speech recognition. The last 3 here, they are mostly used in speech recognition. Actually, the last 3, they are actually called left to right model, but different variants. Like the second one, you can see that you can transit from state 1 to state 2. You can jump. So like what I have in figure 11C here, we see that we say stay. For figure 11C, we can call it stay, move, and skip model. That is, we can either do a self loop, we can stay in state 1, that's in state 1, self loop, or you skip state 2 and move to state 3. And the last one is stay or move model. You can stay in state 1, that's self loop in state 1, or you move from state 1 to state 2. So these are some of the models that are actually used to model speech future. So here we have an idea. We just want to talk about, in the last tutorial class, we talked about how to calculate the initial probability. If you still remember, how to calculate the initial probability, how to calculate the transition probability, how to calculate the emission probability. So how do we get this initial, for the purpose of the ED Markov model, the purpose of the speech recognition or to develop a model is to train the recognition, that's the recognizer, to be able to recognize any spoken word that is fed to it and give the text equivalent of it. So for us to train that ED Markov model, we have to define some parameters. So those parameters, we have what is called, like what I have on this slide here. So here I have this is a 4-state model. So we can see that we have 4 states. We have everything we have on the top row there. They are all states 4, representing state 4. Everything we have on the second row, they are all representing state 3. Everything I have on the second row, that's second to the last, they are all representing state 2. That's the way they will be aligned. Everything we have on the bottom row, they are all representing state 1. So each one of them. So for the training, so what we do there for the training is we move from left, we move towards the right hand, like you are scanning something. So we scan from the left towards the right. When we get to the right, we also scan from the right back to the left. So when we do that, we take note of some parameters or we make some calculations. Let's come back to that. So for each of these states here, we can have what is called the initial probability. If let me just flip this back a bit. Now, here we said here was where we talked about the initial probability. We represented with pi. We said we represent that with pi. So we have pi naught here. We say pi naught equals to 0, 1, 0 here, right? I believe we still remember this. Hello? We still remember this, that we said pi naught equals to 0, 1, 0. And addition to this is this. It can be any value, but what you must take into consideration is the sum of the initial value must be equals to 1. It means I can actually use 0.5, 0.2, and 0.3 for this case here, in this particular spot here. I can use 0.5, 0.3, and 0.2. So you now follow the procedure that we explained in the last class. So this is the initial probability. So in speech recognition, this initial probability that we have here, there are 2 approaches to actually developing it first before you train. So the first approach is what we have here, that we can either do uniform initialization or we do random initialization. In uniform initialization, we give equal probability to all states. So every state has its own initial probability. So if it's a 3 states, for uniform initialization, I'm going to be having 1 divided by 3. If it's a 4 state, I'm going to be having 1 divided by 4, such that every state will be having equal probability. But if it's a random initialization, you write the program such that it will give them random probabilities. And again, the sum of all the probabilities must be equals to 1. That is what that random initialization will do. You must ensure that the sum of the probability equals to 1.
Hello. Gabriel, can you hear me? Maybe you should give room for questions so that you don't lose your audience.
All right, sir. So if I may ask a question now. So my first question is, how do we make choice for the initial probability in speech recognition? Here we said that we have an initial probability here, 0, 1, 0. But in actual speech recognition, how do we make an initial probability? Here we said that we loop it. We continue to multiply this until it converges. It does not change. We now say we have our best initial probability to be used by the Vitabe algorithm. So before we do that training, how do we compute our initial probability for speech recognition based on what I just said? Two approaches. Anyone? Please, anyone? Who is answering the question? How do we compute the initial probabilities? We said there are two ways to compute the initial probability for speech recognition. What are the two ways? Anybody from those online?
Yeah, Gabriel, good evening.
Good evening, sir.
Yeah, you did mention two approaches. One is to have the random one where you assign the probability randomly, and the sum of those probability must be equal to 1. Then the other one is to assign equal probability to each of the three states. And those equal probability two must sum up to 1. One is random, so it can be any probability, but they must sum up to 1. The other one is equal probability.
Okay, so thank you very much, sir. So I can move on. So that is the first one. So we said that for a speech recognition modeling, we have a state represented by transition, initial probabilities. Please, let's take note, please. Represented by initial probabilities, transition probabilities, and emission probabilities. Like what we have here. If you look at what we have on this slide here, on this figure 15 here, we have 3 states here. So we can move from state rainy to state sunny. That is a transition probability. So we can move from state rainy to this observation here, which is sad. That is an emission probability. And each one of them, this rainy, cloudy, and sunny, we have its own initial probability. So in other words, what we are saying is the parameters that we see on this figure 15 here for speech recognition for a start, for the initial probability, we are going to, this initial probability that we have here is 0.2181, 0.2727, 0.5090. They will be obtained using either of those two approaches. That's this parameter that we have here. That's the way they are computed for speech recognition. Then what about this particular pass, this transition part here, like this 0.2, all this green one, all these green pass, 0.3, 0.4, 0.3, 0.4. How are they computed, including 0.7, 0.2, and this last self loop, 0.5? How are they conceived in the first place before the training? So what they do there is similar to that of initial distribution probability. They also use uniform initialization. That's assign equal probability to them. But make sure that in this case, if you are assigning equal probability to them, you must take into consideration that the sum of all the probability leaving a particular node or state must be equal to 1. For instance, if I'm assigning equal probability to them in speech recognition, all this green coming out of this range, this 0.2, 0.4, and 0.3 must sum to 1. Sorry, coming out of range, sorry, we have 0.3, we have 0.2, and we have this green, this red, this self loop, making 0, that's making 1.0. They must be summed to 1. Then this cloudy as well, we have 3 states coming out of it. We have this 0.4, we have this self loop is 0.2, and we have this back loop here coming out of it 0.4. So by the time we add the O3, we are going to have 1.0. So that is the first idea there. So the first idea there is to use a uniform initialization. But that uniform initialization must be such that sum of all the probabilities within a particular state, that's sum of all the probabilities leaving a state, must be equal to 1. Please, let's take that into consideration, please. Then random initialization, just like we said before, we are going to give random values. And we also take into consideration that the sum of all probabilities must be equal to 1. Question. Now, the question is, someone should give us just a conception of values that we could give. Let's assume that this Sunny is representing a particular futures. Let's say it's representing let's say it's representing a phoneme. Let's say it's representing phoneme B. This Sunny is representing B. So who can give us likely probability that we can assign to all these parts leaving this B phoneme? Here we have it as Sunny. That's this 0.7. We don't want this 0.7. We don't want this 0.3. And 0.7 and 0.3. So who can give us an idea? We have just 2 loops coming out of this Sunny. Who can give us an example of value that we could give to using uniform distribution or uniform initialization? From those online, just give us any idea of value that we could use using uniform initialization for that Sunny state.
Do we have anyone that wants to try? Physical participants, online participants? Okay, so we have someone, one of our physical participants now.
We can assign 0.5, 0.5.
Yeah, thank you very much. That's very right. So what of if you want to use random initialization?
We can assign 0.2, 0.8.
0.2, 0.8. Let's clap for him, please. So that's very correct.
Thank
so
you.
That is that. So the third one here, I don't want to talk about that one yet. So the third one that we have for the initial, so I will not talk about this yet. So for the emission probability as well, for the emission probability, we don't use uniform initialization, neither do we use random initialization. We do our calculations. How do we do that calculations? Don't forget that we said that within each, if you look at what we have here, this is a picture of, this is a spectrogram here. This is a spectrogram feature here. So we can see some observation here. Observation. We have the observation 1 up to 9. And we have some phonemes representative of this observation. So this is a phoneme model with let me say end state because there is a continuation here. So when we have each of these features is a 39 MFCC. 39 MFCC. So this 01 is representing 39 MFCC, 02 is representing 39 MFCC, 03 is representing 39 MFCC. So we now need to distribute. So we can have 01, 02, 03 distributed inside this. Like what we have here. You can see that 01, 02, and 03, they are all representing phoneme E. That's letter I. But each one of them will be having different attributes. For instance, maybe this one is characterizing the beginning of that phoneme. Maybe this one is characterizing the spectrum, maybe it's characterizing the noise associated with this phoneme high. Maybe this one is characterizing the accent representing this phoneme high. So for us to distribute this inside this particular state here, that's where we use Gaussian mixture model. It's like a clustering approach. So what it's going to do there is it's going to cluster, put them in different clusters based on their similar attributes. So when you cluster them, when you see that, okay, this one and this one, maybe 01 and 02, they have the same attribute, put them in the same place. Maybe 03 is having a different attribute, put it in another cluster. So each of, let's say we use a Gaussian mixture model with a mixture component of 3, or let's say 3 clusters. So it's going to have 3 mixture components. So each of the mixture components will be characterized by the weights, the mean, and the variance they have in that particular distribution. So the weight, the mean, and the variance is what we now use to calculate the initial emission probability. So if you now want to calculate the emission probability of this particular observation within this particular state here, I'm going to use the Gaussian parameters within this state here to compute that. And that is what we have on this slide there. So we can see here that we have Wj equals to 1 over 2 pi square, 1 over square root of 2 pi zeta raised power 2. This is actually a Gaussian distribution. So here we compute the weight. You use this to compute the weight of that. And when you compute the weight of that, and this Bj of x of t is the observation probability that we need in our ED Markov model that we must have developed. So how do we compute that? So this weight that we compute here, this Wj, that we compute using the mean and the variance, we now multiply it by the distribution of the Gaussian distribution within that particular state. So here, so when we compute that, when we multiply these two, we sum it. We can see that we are summing it from k equals to 1 to k equals to k. So this k that we have here is total number of mixture components. Let's say we have 3 different clusters. So this last k here at the top here will be 3. So it will be from 1 to 3. So each of the cluster will be having its own weight. So this Cj of k, this Cj of k is representing a weight. Is representing weight. Is an equivalent of this Wj. So we'll multiply by its distribution within that. And when we do that for the second mixture component. So in other words, to calculate the initial emission probability, we make use of the parameters of the mixture component within that particular state to actually compute that. But a question is, how do we know, or how are we sure that the weight, the mean, and the variance of each of those mixture components is the correct one we are supposed to use to compute that emission probability? We know that because we also train that distribution of that Gaussian within that state. So we train that using the expectation maximization algorithm. The expectation maximization algorithm, what's going to do there is going to ensure that we get the correct weight for each mixture, we get the correct variance for each mixture, and we get the correct mean for each mixture. So that's how we get the initialization for our emission probability. So after we must have gotten that initialization, we now use those parameters to train our model. That is what we have on this slide there. So here we have our forward. So we now use what is called the Baum-Wedge expectation maximization algorithm. How does it work? So the way it works is this. The initial distribution or the initial probability that we specify is this by high that we have here. This Bi of y of 1 is the initial emission probability that we just calculated using that formula there. So we now do what is called forward movement. We do what is called backward movement, or what is called is like a scanning. Sorry, that was from the microphone. So we now do what is called the forward scanning, and what we also do what is called the backward scanning. So for the forward scanning, it's actually what is called forward algorithm. That's what we are going to look into now. So for the forward scanning, we are going to use that initial probability, the emission probability that we calculated, that we must have calculated before. We use it together with the initial transition probability that we said we just get out of conception here, either uniform initialization, we use random initialization. We use it together with this and do what is called forward scanning. Forward scanning is like, if you look at this picture here, on this slide here, we can see that we have on the first row, we have first row representing state 4. Second row is representing state 3. The next one is representing state 2. And the next one is representing state 1. And what we have at the bottom here is at different time instants. So at time instant 1, time instant 2, 3, 4, 5, 6, 7, 8, 9, 10. So this time instant will be depending on the number of observations that we have. So let's say we have speech feature. This speech feature that we have here, this speech feature that we have, let's say 0 to 9. This is 0 to 9 speech features. So it means that I'm going to be having 9. I'm going to have it from 0 to same length. That's 1 to 10. It's still going to be 1 to, but it's going to be from 1 to 10 for that. So when I have that, I'm now going to create some parts. So this part here is actually with respect to the relationship between the states. So this diagram that we have here is a representative of the figure 11D that we saw before. This diagram here. If you look at this figure 11D, we can see that we can traverse from 1 to 2. We can go from 2 to 3. We can go from 3 to 4. We can also do self-loop within each loop. So that is why here we have it that when we start from 1, we can go from 1 to 2. We can go from 1 to 2 at the bottom here. We can go from 2 to 2. We can go from 2 to 2. Sorry, we can go from 1, this one here. We can go from this 1 to this 2. We can go from this 2 to this 3. But we cannot go from, like what we have inside this place here. We can't go from, this is state 4. We can't go from state 4 back to state 3. There was no path in that diagram. From state 4 to state 3, there is no backward path in this diagram here. So that is why we are not having a path from state 3, like from here, backward. I hope you are getting that. That's the reason why we are not having it backward here. So the diagram that we have here is replica of what we have in 11D here. So we now do forward scanning and we do backward scanning. So when we do that, we take some parameters. So this is the forward scanning. We represent it by alpha. We do backward scanning. We represent it by beta. So when we do that, we now update. We get some parameter. The first parameter we get there is what is called, a question. The question is, what is the first thing that we are going to do after we have gotten our initialized value? Somebody should tell us, please, quickly. After we must have gotten our initial value, what's the first thing we'll do from the estimation step? Anyone? So,
do we have anyone online participants?
okay, maybe I should repeat what I said before. So when we get those initial value, either a random distribution or uniform distribution or uniform value, or we do the one of calculation using the emission probability, we now do what is called the forward pass or forward scanning and backward scanning. Forward scanning is represented by alpha. We're going to see how we do it. Backward scanning is represented by beta. So when we calculate the alpha and the beta, we now calculate what is called the state occupation probability. This gamma high is representing state occupation probability. And this zeta high, this zeta ij of t is representing the state transition probability. What it means is this gamma high, what it means is what is the probability of being in a particular state? That is here. All these small circle here, they are represented by states. Like if I am in this state, for instance, where we have the pointer here. If I am in this pointer here, what's the probability of being in this state for a number of steps? For instance, we are supposed to have an observation at the bottom here. Observation at the bottom, like what we have in this place here. What we have here, we have observation, then we have our states. So when we have that, what's the probability that at this time step, and what's the probability that for how long I'm going to remain at this particular arc or at this particular state? Why some observations are coming from the left and observations are coming from the right. That is the gamma high. Then that's zeta ij. What it means is if I move from this state to this state, what is the probability that the other observations are coming from the left, observations are coming from the right? The way I can explain this is this. Let's say you are a policeman at a checkpoint. If you are a policeman at a checkpoint, there are times that you need to make movements because probably some enemies, maybe you are fighting some criminals and you are targeting each other. There are some times that for you to know what will happen, you need to leave your zone where you are. Maybe you just need to move out of where you sit or where you stay. Why? Because while you are watching your left, while you are watching your right, at that point you might need to move, because if you don't move, a bullet can come and hit the person. That is what the transition, this zeta ij of t, that is what is doing there. That is, if I'm moving from state I to state J, what will happen to every other observations before that state, before that movement, and what will happen to the every other observations after that movement? That's what that one is doing. Then this particular one here, gamma I of t, what it means is, if I remain in this state, what is the observation coming before and what is the observation coming after? So how long must I remain in this state, considering the observation coming before and observation coming after? So I can liken that one to a policeman. Then there are some times as well, you may not need to leave where you are sitting while you are watching your left and your right, because if you move at that point again, you might be a victim of targets. That is what these two, they are actually doing. And when you can compute these two, we now come here, which is the maximization step. So at the maximization step, we now calculate our new pi. You know, before we said that to get the correct pi here, you know, this is just a general explanation. We said that we iterate by multiplying the initial pi with the matrix, right? We multiply the initial pi with the matrix and we'll continue that multiplication until it converges, such that what you have on the right here is replica of what we have on the left here. But here, this is just a general overview of it. But in speech recognition, we calculate the new pi using the state occupation probability. That's what's probability of being in this state. For how long will I be in this state? Or state transition probability. For how long can I transit from state I to state J? That is the state transition probability. So we use that. So we use only this state transition. So for how long must I remain in that particular state while I am scanning left and I am scanning right? That is this pi. That's the new pi we have gotten here. So to get the new transition probability for each of those states, that's, for instance, here we have states 1, 2, 3, 4. That's between that. So here we are going to have A12, we are going to have A11, A22, A23, A33, A34, and A44. So we now compute new parameters using this particular formula we have here. So I don't want to waste time on that because I still have some other thing I want to talk about. So we also compute our beta, which is emission probability, using the gamma I of t. So when we get this, we repeat. So this is over this one training instance. So what we have here from t equals to 1 to t equals to 10 is one training instance. So that is one iteration. So after this one iteration, we get our pi value, we get the transition value, and we get the emission value. So we repeat this step. So for the second iteration, we are going to initialize. So this alpha I of 1 will be taking the just computed pi value that we have here. It will come in here. And this new b value that we have, we also come in here. So we'll follow the same process again. And we'll follow that till we get a situation whereby the value of pi does not change. The value of AI for each of those transition states, for each of those parts, does not change. And the value of B for each of the emission also does not change. That is when we stop the algorithm. So here is an overview of the forward algorithm. So here, what we have here is the forward algorithm. So how do we calculate the alpha in the real sense? So here, we'll be using this idea here. So here we have 3 states. So here we have a state with 3 observations. We have 3 observations. We have movie, book, and party. So you can see here that we are actually moving in the forward direction. We are moving from H. So what we are going to do there is, if we have 2 states, this is actually a 2 states. We have happy and sad. We have happy and sad. So the probability of happy given happy is 0.99. Probability of sad given happy is 0.01. Probability of happy given sad is 0.1. Probability of sad given sad is 0.9. So we are going to, so if the observation, so if we have a two states, we are going to have happy, happy. We are going to have happy, happy, happy at the top. So we are using 3 because we have three observations: movie, book, and party. And at the bottom, you put the second one there. But let's assume that this is a 3 state. This is a 3 by 3 AD Markov model. Let's say we have another state here. Let's say this is angry states. So it means that we are going to have another one at the bottom here. Probably this will shift, this SSS will shift to the bottom while we have another one at the middle here. So we can see here that every part in this particular diagram here is connected, unlike what we have initially here, where we have some parts not connected. We can see that there is no part from this particular arc backward like this to this arc. There is no parts there because there was no transition from the original diagram itself. There was no part from 3 to 2. So, but for this particular one here, we have parts. We have parts from 1 to 2. We have parts from H to S, and we also have parts from S to H. So what we do there is we move in the forward direction. Let me just say that for now. We move in the forward direction and compute some parameters. So parameters of each block, they are represented by alpha. So here is alpha 1. Here, this is alpha 2. This is alpha 1. This is alpha 2. This is alpha 1. This is alpha 2. I can call this alpha 1 at time instance 1. Alpha 2 at time instance 1. Alpha 1 at time instance 2. After 2 at time instance 2. After alpha 1 at time instance 3. Alpha 2 at time instance 3. So that's what we do in forward algorithm. We are going to see that now. Then the backward algorithm, we go backwards. Though we are still going to use the same path probabilities, just like what we have here. But we are going backward from the last state. That's from t equals to 3, like what we have here. We are going backward. That's what we do in backward algorithm, backward scanning. But we now do something there. The initialization that we do here is we assume that each of these blocks, the starting point is having beta equals to 1. That's what we have in the algorithm here. This is what we have here, beta equals to 1. So that's why we have this to be 1. Actually, this will be 1, and this will also be 1. Unlike here, where we started with their initial probability, that's 0.8 and 0.2. That's the initial probability that we started with here. But in Vita B, how do we use Vita B? Let's say we have a particular sequence. Let's say we have a particular observation, like the observation we have here, movie, book, party. We want to get the correct sequence that actually that is replica of this movie, book, party. So we have H, we have S. So what we do is, in the case of forward algorithm that we have here, at each of these blocks, we take the sum of every part entering it. For instance, it's just a single part. So it's just one part. At this particular point here, we take the sum of this. We multiply this 0.16 by this, what we have here. And we multiply this 0.12 by this, what we have here, by this 0.08. We sum them and we get the representation of this particular arc. We stop at that particular arc. So what we do next is, so at this point here, so we now have our so at the Vita B, for the case of Vita B, instead of summing them, the difference between Vita B and forward algorithm is that instead of summing them, it's the same approach. Instead of summing them at this point, we'll find the maximum of the two. Maximum of this, and this. So the maximum of the two, we now multiply it. So if the maximum is this, we multiply by this 0.08, and we have a representation of alpha for this particular state here. If the maximum is this, we multiply this by 0.016. So we have a representation for this arc here, which is state H. That's what we do in Vita B algorithm. So this is an illustration of the Vita B algorithm, forward algorithm. So I will just quickly explain what is happening here. So we have an idea of this. It's not difficult. So we have a model here. This is an AD Markov model, 2 states. We have state rainy and we have state sunny. So state rainy, state sunny. So There is a safe loop 0.5. I can move out of rainy 0.5. There is a safe loop is 0.7. I can go from sunny to rainy 0.3. I can go. So I have two observations here: observation sad and observation happy. So the question can be, what is the probability of sad being sad, given that it is raining? That is 0.8. I believe we still remember this. What's probability of being happy, given that it is raining? That's 0.2. And don't forget that we said before that when you are choosing initial value, we get 0. You can use any value. You can use maybe random initialization or use uniform initialization. But again, what I'm having here, the parameters I'm having here, I'm assuming that these are parameters, they are trained parameters that have been obtained. They are optimized parameters, because without you getting optimized parameter, there is no how you can do your decoding search. So for you to do your decoding search of the correct sequence for that particular observation, that is where the Vitabi algorithm comes into play. So you must have trained your model using the Baumwedge expectation maximization algorithm. Then you now do your Vitabi decoding search. So this is a two states. So here, this is the representation of that state. So when we look at what we have here, so we have three observations that we are trying to predict: sad, sad, happy. So what particular sequence actually give rise to this sad, sad, happy? For this sad, sad, happy, we can have quite a number of sequences. We can have RRR, we can have RRS, we can have RSR. For instance, in speech for this model, for ED Markov model, the total number of observations is always the number of states raised to power the number of observations. For instance, here, the number of states is 2 states. The number of observations is 3. So the maximum number of states I'm going to have will be 2 raised to power 3. That's 8. So if you do the permutation of this, you are going to be having 8 different sequences. 8 different sequences. And as the number of states increases, like what they do in speech recognition, we have many states that are compressing together. So you cannot be doing that. So you have to do an optimized, you have to use an optimized algorithm, and that's where the Vitabi comes into play. So how do we start? We start with an initial probability. So the initial probability, so we are using red, so we are going to use rain, and use sunny, because you have two states. Assuming we have another state there, maybe cloudy, there will be another state here, which we carry CCC. So what we now do there is we compute the probability of each of these blocks. How do we compute the probability? The first one there is having a state of sad. We use the initial value. What we have here is, from this algorithm here, we have our alpha 1 of j equals to pi j multiplied by bj of x. So the alpha 1 is this state here. This particular block here, this block is alpha 1 of t. This block is alpha 1, alpha 2 of t. This is alpha 1 when t equals to 2. Alpha 2 when t equals to 2. Alpha 1 when t equals to 3. Alpha 2 when t equals to 3. So we now do recursive dynamic programming. How do we do dynamic programming here? When you compute the value of alpha 1 and alpha 2 at time instant 1 for this observation, how do we compute that? That's what we have on this slide there. We take the probability of R. We take, that's what we have here. We have the probability of R. That's what we have here for Ford algorithm. You take actually Ford algorithm and mixing them with Vitabi. It's the same approach. Like I said before, when I explained the previous diagram, I said that at this point, that's where the difference comes into play. Instead of summing for Ford algorithm, for Vitabi, we find the maximum of the two paths. So for the Ford algorithm, to calculate the first part here, this first alpha here, we take the probability of this R, probability of raining. I will now find out what will be the probability of sad given that it is raining. Probability of sad given rain is 0.8 from that emission matrix. So multiply by that is 0.375. We have this 0.3. We also take probability of sad given that it is sunny, which is 0.4, and multiply by the initial probability of 0.8 is there initial probability of Sunny, which is 0.625. Don't forget that this initial probability that we are using here, this 0.625 and 0.375. Okay, let me ask you a question. How do you think you must have gotten this 0.375 and 0.625 in the case of speech recognition? I need an answer to that. How do we get this 0.375 and 0.625 in speech recognition modeling, the initial probability? Because that is what we are using for our decoding search now. So how are we sure that these values are correct?
Hello, can you hear me? This sum is equal to 1.
Not really. Who can answer the question?
Anyone want to try?
How are we sure that what we have here is 0.375 and 0.625 in the case of speech recognition is the right one we are going to use for the decoding search? Anyone? From those online, who can answer that question? Okay, let's leave that. Well, actually, I was sure that that is actually right is because we have trained it. And don't forget that before we can pick this value, it must have converged to these values here. So it means that the value is not changing from this 0.375 and it's not changing from 0.625. So we now compute this. So this 0.3 and 0.25 that we have here, they are the alpha value. They are the alpha 1 and alpha 2 at time instance 1. So we now, for the second block here, this R and S here, we now compute the probability at this point. We calculate the alpha 1 and the alpha 2 at this particular point here. How do we compute this? If we go back to this formula, the formula that we have here, we have summation from I to n of alpha t minus 1 of I, A of ij, and B of j, multiplied by B of j. So what we do there is our alpha t minus 1 is the previous one that we have here. Like in this case here that we have here, let me use this. Like in the previous case that we have here, we have 0.16. So 0.16 here is coming from this pass here. So for each summing point, this alpha t can be likened to alpha 1 of time instant. This j is actually time instant 2 in this case here. This alpha t is alpha 1 from the top here. So from there, we now sum the previous alpha 1 at time instant 1 multiplied by the transition probability, which is this value here, by the emission probability, which is this 0.2. This bj of x of t is the emission probability. You can see that there is a summing point here over all the states. So this is one state that is entering it. That's all the states entering it. This is second state entering it. So from the second state entering it, this alpha t minus 1 will be alpha 2. Alpha 2 at time instant 1. That's 0.08. We'll multiply by the state transition matrix, transition probability, which is 0.1. That's probability of H given S, which in this case, probability of H given X is 0.1. We'll multiply it by the emission probability. That's probability of the emission here. What's probability of reading book? Provided that somebody is happy. Reading book, that's here. Provided that somebody is happy, that's 0.2. Multiply by 0.2. And when we do that, we add them together. That is what is actually happening here. So, and that is what I have incorporated for this particular task here. So we can see here that here, to get this 0.18, I used this 0.3. This 0.3 is this value here. And I use this 0.28, which is sorry. To compute the 0.18, we use 0.3, which is this guy here, and 0.4, which is this part here. How do we get this part? This part is actually joining that Aij and B of J. That is what this 0.4 is joining. And that is what I have actually computed. Let me see. That's what I computed here. 0.4 that I have here. That's probability of SAD given rainy multiplied by probability of rainy given rainy. That's how we got 0.4. Probability of SAD given rainy is 0.8. Probability of rainy given rainy is 0.5. So you always use the emission probability by the transition probability to get the pass probability. So when you get that, you now multiply by the previous alpha, which is what I have done here to get my 0.18. Then here, so we also do the same thing from the bottom here. You do 0.25, multiply by the pass probability. You follow the same approach. It's well explanatory from here. You follow the same approach, 0.25 multiplied by 0.24. You now add the 2. So when you add the 2 is what we have here. But instead of adding, for the case of Vitabi algorithm that we have here is Vitabi algorithm. You can see that instead of adding, here we have 0.24 times 0.25, 0.4 times 0.3. That's block 2 top R. Block 2 top R. Here, you can see that instead of adding here, you can see what we did there. We picked maximum of the 2. So here, the maximum of these 2 is 0.12. That is why we picked the maximum, which is 0.12. But if it is forward algorithm, we had the 2. That is where the difference is. So this, what I have done here, we also follow the same approach at this bottom here. So here comes the question. How do we get 0.20? This 0, so forget that each of these path probabilities is joining this AI of J and this BJ. So who can just tell us how we got this 0.2? Who can tell us how we got 0.2? Okay, I've just been told now that I have just 2 minutes left. Who can tell us? No one. So if you follow the same approach, we take probability of SAD, probability of sunny given rainy, probability of sunny given rainy. That's what we have here, which is 0.5. Multiply by probability of SAD given sunny, which is 0.4. We multiply the 2 and we have 0.2. So we also follow the same thing. So 2 paths are actually entering this. So we multiply. So we now multiply 0.2 by 0.3. We multiply 0.25 by this, and we get our value here. So when we now do the same thing, we do the same thing here, we get our value. So what we now do next is we now pick the maximum from each of those alpha 1 and alpha 2 for each of those states as they are arranged the way they are here. So the maximum here is 0.3. The maximum here is 0.18, representing her here. The maximum here is 0.1086, representing hers. So it means that out of all those 8 permutations of RRS, the part that is replica of this observation sad happy is actually rainy, sunny. So now you backtrace it from here. Actually, when you write the algorithm, you must have stored the maximum in another list entirely, such that you now backtrace it and pick that maximum word pass. But in the case of forward algorithm, what we do, it will also give you the sequence for the forward algorithm, but the purpose of the forward algorithm is to compute the summation of all those 8 sequences that we have for this particular observation. So the sum is always the addition of the last alpha 1 and the last alpha 2, depending on the number that we have here. So it means that the sum of all the states here, the sum of all the sequences for this observation will be 0.0258 plus 0.1086. Why the sequence with the correct observation, with the correct sequence for this particular observation will be rainy, sunny. So you can see that the forward algorithm is giving us the sequence and it's also giving us the sum. Why the vector B is giving us just the sequence. But the backward algorithm is what we have here. We go backward, the same approach. It's well explanatory from this note. But we start with 1. Like I said initially, we start with 1. We now compute it. We compute it recursively backward. So here, to get 0.4, we multiply 1. We use the same path probabilities. We use the same path probability. We multiply this 1 by 0.3. We get multiply by 0.3. So here, there are 2 that are entering this block here. So we have 0.1 multiplied by 1. You add it to multiplication of 0.3 multiplied by 1. You get this particular 0.4 here. To get this place here, you multiply 0.42 by 1 plus 0.06 by 1. You get this one here. And to get this place here, you multiply 0.48 by 0.2. You add it to 0.4 by 0.4. You have this part. So these are the values using the backward algorithm. And how will you be sure that your computation is very right? How you be sure the computation is very right is this. If you come to here, the alpha 1, the forward and the backward algorithm, at any time instant, I'm going to stop here. I want you to take note of this. At every time instant, this is forward algorithm. At the first state here, we have 0.3, alpha 1. We have 0.25, alpha 1, alpha 2, at both at state 1. We have 0.3, we have 0.25. So 0.3 will multiply corresponding block in the backward algorithm. 0.25 will multiply corresponding block in the backward algorithm. So 0.3 will multiply this 0.256. And the second one will multiply 0.2304. So when you do that, that is what I have. Let me see if I have it somewhere. Okay, I don't have it here.
Hello.
So if you do that, few minutes.
Mr. Sobola, we need to round up now.
So I'm rounding up. So when you do that, when you multiply 0.256 by that is 0.3 that will have it, and you multiply 0.2304 by this 0.256, and you add the 2, you must get, please take note, please. You must get the sum of all the sequences for that observation. So in other words, you must get 0.0258 plus 0.1086. If you do the same thing at this point here, multiply 0.18 at any time instant on that block for the product of alpha and beta, and you sum it over all the states, you always get the sum value of all sequences for that particular observations. So that is where stop. Thank you very much.
Thank you. Thank you. A round of applause for Mr. Sobola. Thank you so much, sir. I know if we'll allow you go on, we're going to be here till tomorrow, but at the same time, we're trying so much not to divert from the goal of this program. You know, this is a tutorial. We want people to actually learn. We want them to understand. We are moving from it's not the normal class, what's it called now? Lectures in class. The student just sits down and listen, and probably some of them might. This tutorial, we want everyone. For this tutorial, we want to actually impart knowledge. We want to impart knowledge. So once again, thank you, Mr. Sobola. That was very good. That was insightful. Yeah, so it's 7 already, but please, we need to take questions. Please, if you have questions, online participants, physical participants, within the next 10 minutes, we're going to round up. We're so sorry. Online participant, please, do you have any question? Maybe question from last session, question from today's session. Online participant, physical participant, do we have any question for Mr. Sobola?
Well, just to commend Sobola for a very good presentation, and to probably seek a clarification on figure 10. Can you quickly scroll back there? Figure 10. When you're talking about a matrix A. Okay, then go to the next slide, or the slide before this. We're talking about a matrix, okay, where you're giving this example. Yeah, number one, I just want to be double sure and to clarify that iterations can be interpreted to be transition. And that is why we can have a loop on the state. Is that correct?
No, sir. Iteration here is actually used for training. Why transition? You transit as many times as possible within a particular iteration. So iteration is just a training token, is a training step. So you can have as many iterations that you have. So within each training time step, so you can have as many transitions. For instance, in an ED markup model, because the model is very complex, you have many transitions inside of it. Like the diagram I showed, that one that has forward and backward, that I said you scan leftward and you scan rightward. So you can have as many transitions inside of it, depending on the number of observations and the number of states that you use to model your HMM.
Okay, I'm asking this question because of this P02 for a time step of 2 that you explained on this
All right.
slide.
So if I may want to explain this, so what this thing means is I'll come back here.
No, I understand here. Now
I want to show you something here, sir.
Go back to that figure 10.
Okay, sir.
Figure 10. Okay, so if I'm to move from state 0 to state 2 in a time step of 2 steps, so I can decide to go A naught naught as a loop 1.
Loop. Yes, sir.
Then multiply by A02. Is that correct?
Exactly, sir. Yes, sir.
Okay. Now go back to the next.
That's one out of many options.
Yeah, so that's what I just wanted you to also point out, because this example that you give, you will say that this option of iterating on a particular distance might not probably be showing there. You understand?
I didn't get, sir.
Okay, it's one of the options. That's what I just want to clarify. No problem.
Okay, thank you, sir.
Yeah.
Thank you so much, Dr. Taufik. Thank you, sir. Do we have any other question from online participants? Do we have any other question? Do you need clarification? Do you need Mr. Sobola to shed more light on something that seems confusing? Okay, so we just have comments from Mrs. Comfort Shomefon. Well done, sir. Okay, so in the absence of more questions, we would like to say thank you. Thank you so much for joining us again today. And one more time, can we put our hands together for Mr. Sobola? Thank you. You know, when you're giving your favorite meal, you won't even know when you're full. So this is Mr. Sobola's its area. So if you permit him, if you leave him, we'll be here till next year. Okay, so Mr. Sobola, we're very grateful. Thank you so much for sharing with us out of the a very deep well of knowledge. We appreciate, and we'll say God will continue to fill you more and more and more. We hope we'll have you on board on this tutorial again, maybe next edition. Okay, so moving on to our closing remarks now from Prof. I don't know if Dr. Oshin has something to say just to wrap up, because I think this is the last of your series. So just something to say to us.
All right. So thank you everyone for being here. I mean, like she said, this could have gone on and on for another 2 hours, perhaps. But I think we've been able to get something today. At least I did. So that's the important thing, that it's value adding. All right. So thank you so much.
Thank you, Ma. Yeah. So now to closing remarks, Prof.
Okay. Yeah. It's been so exciting for me. I'll call this an intellectual banquet. And I'm sure you are getting it. You're hearing me.
Yes, we can
This
hear
is
you,
very
sir.
rich, and we have the chef in the house, the chefs in the house are doing justice to the topic beautifully. So thank you and well done, Sobola. Well done. More grace to you, and thanks, Dr. Oshin, for the combined effort. Okay, you are really rich, and I can assure us that this is going to go online. The one we had last week is already online. We've posted the link to the ASPMIR platform. So I think the beauty will come out if you're able to sync the previous one with this current one. And we are going somewhere with this mathematical foundation for sequence modeling, but we haven't gotten there. So gotten there because the whole idea of laying the statistical background. So we've not really, this HMM is a statistical sequence modeling method. Okay, but the topic of this particular session of the tutorial is mathematical foundations of artificial intelligence. So we still need to get there. And that's why I think there will still be one more session from Sobola and Dr. Oshin, which is going to, we weaving this into recurrent neural network now for automatic speech recognition. That is where we're going. And I'm sure this foundation is to compare what the RNN and the different variants, what it can do beyond HMM. Okay, so that's actually the target. But these foundations, I think, have been very rigorous, mathematically so, which is beautiful. So justice has been done, and I appreciate that a lot. Thank you, everyone, for listening. God bless the facilitators. God bless everyone in attendance. Thank you, Dr. Taufik, for being part of this. One of his friends also joined us, an associate professor from Korea, I think. So, and the presence is well appreciated. So thanks, everyone. Helmi, thank you for the job well done. And everybody that has made this a success. God bless us all. Thank you.
Amen. Thank you so much, sir. Yeah. Okay, so now to the closing prayer. Yeah, a few announcements before we say the closing prayer. So as we all know, this is a recurring event. So we're going to have this next month by God's grace, same time. If we need to change the link, we'll send it across to us. So, and another thing is we have a platform, we have a WhatsApp platform. So if there is a particular topic that you actually want us to dwell on, because like I said, this is a tutorial. The main goal is to impart knowledge, to help students to go to the foundation, fundamentals, beyond the surface. We are going deep so that you have deeper understanding. When you come across any model, you have like background knowledge of what it's doing and what is going on there. So if there is any area you might be facing, maybe your work or something, you can put it on the chat. Please, if you're not on the WhatsApp chat, you can just send a message on this Zoom chat. We'll add you immediately. So here, I just needed to mention that. Thank you one more time, our online participants, our physical participants, because there wouldn't be this program without you guys. We're very grateful. Thank you. We hope to see you again next month. Okay, so now for the closing prayer. Mr. Uche, this closing prayer.
Let's be in the mood of prayer. Heavenly Father, we worship you. We thank you for this wonderful monthly tutorial. We give you all the honor, all the glory for making this program possible. We've been able to disseminate knowledge. We've also gained a couple of things individually. Father, help us retain those content, and those content will help us advance our work in various areas of research in Jesus' name. Father, our Lord, will help us to give us more insights as more programs begin to unfold, that it becomes richer, it becomes better, and it becomes more impactful in the lives of students in Jesus' name. Help us as we go on our various homes. You shall see us through. And at the end of the day, we'll have focus to glorify your name in Jesus' name. Empower our PI and empower our LOCs and all academic experts on this particular research group, that they would more insight and more progress as they move the group forward in Jesus' name. Thank you, Lord. We give you the glory. In Jesus' name we prayed. Amen.